In this video, we will be looking at combinations and compositions of functions. So what this is going to be looking at are different ways to put functions together. We're going to start by looking at combinations of functions, and what we're going to be able to do is use operations on functions as wholes. So f plus g of x is equal to f of x plus g of x. F minus g evaluated at x is f of x minus g of x. F times g of x is equal to f of x times g of x. And then f over g of x is equal to f of x over g of x, provided that g of x is not equal to 0. So you may wonder how this is even important. It might seem obvious, but as we go along into the next couple slides, you might realize how important this really is. So first up, we have if f of x is equal to 2x minus 1 and g of x is equal to x plus 5, find f plus g of x, f minus g of 2, fg of x, and f over g of negative 1. So starting off with f plus g of x, according to that last slide, we can break this into f of x plus g of x. So that'll be my f of x, 2x minus 1, plus my g of x, x plus 5. All I got to do is combine my like terms, and I'm looking at 3x plus 4. And you may not see anything special yet, but just hold on. Next up, we're looking at f minus g of 2. Well, according to that last slide, that's going to be the same as f of 2 minus g of 2. So if I plug in 2 to the f function, and I plug in 2 to the g function, see what I get out, and then subtract them, I should get the right value here. So f of 2, let's figure out what that looks like. That's equal to 2 times 2 minus 1. That's 4 minus 1, which is 3. And g of 2 is equal to 2 plus 5, which is 7. So I'm looking at 3 minus 7, which is a negative 4. Now wait a minute. I should be able to find the full function f minus g of x and then plug in 2, and I should get the same value. Let's see what happens. So if I take f of x minus g of x, that'll give me 2x minus 1 minus, in parentheses, x plus 5. So that's 2x minus 1 minus x minus 5, which is x minus 6. If I plug in 2 to this, I'm going to get a negative 4. So what I'm saying here is f minus g of 2 was equal to f of 2 minus g of 2, but it was also equal to the function f minus g of x evaluated at 2. So there are going to be times where it's easier to plug in your value into each function and simplify it that way. Other times it might be easier to find the function in terms of x and then go and plug it in. So to see it this way, we have f minus g of 2 would be equal to 2 minus 6, which is a negative 4. Next up, we're going to look at f times g of x. Now, according to the last slide, that's going to be f of x times g of x. So we're looking at 2x minus 1 times x plus 5. I need to FOIL that out, and I'll get a 2x squared plus 10x minus x minus 5. And if I combine my like terms, that's 2x squared plus 9x minus 5. For this last one, we're looking at f over g of -1. We can solve it both ways like we did the second problem. So you'll notice the first and third had us solving in terms of x, whereas the second and fourth problems have us solving by evaluating at an actual value. So if we plug in -1 to f, that'll give us 2 times -1 minus 1. -2 minus 1 is a -3. And if I plug in a -1 into g, I'll get -1 plus 5, which is 4. So if I look at this as f of -1 over g of -1, that'll give me -3 over +4. That's a perfectly acceptable way to do it. Or we could look at f over g of x, and that would be our f of x, 2x minus 1, over our g of x, x plus 5, and then plug in -1 this way. So f over g evaluated at -1, we'd be plugging in the -1 to our numerator, which we already said is -3. Then we'd be plugging in -1 to our denominator, which is a +4. So either way you get the same answer, you just have to be careful and check whether you are solving for the function in terms of x, or if you are evaluating at a certain value that you want to know the value for. We're going to look at two more. We're given if f of x is equal to x squared plus 10x plus 16, and g of x is equal to x squared plus 5x plus 6, we want to find f plus g of 4, and we want to find f over g of x. So starting with f plus g of 4, you may have noticed at this point, it's usually easier to plug your value into each function separately and then combine them. So I'm going to find out what f of 4 is. That'll be equal to 4 squared plus 10 times 4 plus 16. That's 16 plus 40, which is 56, plus another 16 would be 72. And then g of 4 will be equal to 4 squared plus 5 times 4 plus 6, which is 16 plus 20, which is 36, plus another 6 should be 42. So when I'm looking for f plus g of 4, I can take f of 4 plus g of 4, which is 72 plus 42. That's 114. So when we're evaluating at an actual number, we should get a number answer out. For the next one, we want to find f over g of x, which means I can look at it as f of x over g of x, which is x squared plus 10x plus 16 over x squared plus 5x plus 6. But as we learned earlier in this unit, it's best to simplify our rational expressions if we can. So I'm going to factor these and see if anything reduces. My numerator is going to factor into x plus 8 times x plus 2. My denominator is going to factor into x plus 3 times x plus 2. The x plus 2's divide out, and I'm left with x plus 8 over x plus 3. That is the simplified version of f over g of x. So far we've been looking at combinations of functions, which just means we're adding them, subtracting them, multiplying them, dividing them. What we're going to look at next are composite functions. Function composition is applying one function to the result of another. For example, if we want to take the result of g of x and plug it into the function f, it would look like f of g of x or f composite with g of x. I'll usually read this as f of g of x. What we're going to do is we're going to start on the inside and work our way out. So we're being told if f of x is equal to 3x negative 3x plus 4, and g of x equals 2x minus 5. Find f of g of 1. I want to start on the inside, which is the g of 1. So I'm going to find g of 1. That'll be equal to 2 times 1 minus 5. 2 minus 5 is a negative 3. Now I want to take what g of 1 is and replace it with a negative 3. So where this g of 1 is now a negative 3, and I'm looking at f of negative 3. So if I plug in negative 3 to f, that'll be negative 3 times negative 3 plus 4. 9 plus 4 is 13. So what that means is f of g of 1 is equal to 13. Next up, we're looking at g of f of negative 3. So again, we want to start on the inside. F of negative 3. Hey, we already found that. F of negative 3 was equal to 13. Now I want to take that f of negative 3, replace it with a 13, and that means I'm finding g of 13. That'll be equal to 2 times 13 minus 5. 26 minus 5 is 21. So g of f of negative 3 is equal to 21. For the next one, we're looking at f of 0. We're still going to do the exact same steps. First up, we want f of 0, because we're starting on the inside. F of 0 is equal to negative 3 times 0 plus 4, which is 4. So I'm going to replace my inside f of 0 here with a 4. And I want to find f of 4, which is equal to negative 3 times 4 plus 4. Negative 12 plus 4 is a negative 8. So f of 0 is a negative 8. For the last one, we're looking at f of g of x. So this time, we don't have numbers that we're substituting in. We're dealing with the functions as wholes. I know what g of x is. G of x is 2x minus 5. So I'm going to replace the g of x in parentheses here with 2x minus 5. That means I'm trying to find f of 2x minus 5. But what have I been doing so far? If I wanted to find f of 0, I plugged in 0 in parentheses. If I wanted g of 13, I plugged in 13 into the function g in parentheses. So this time, I'm going to replace the x's in the function f with a 2x minus 5 in parentheses. So wherever I see an x, it's now going to be a 2x minus 5 in parentheses. So I have a negative 3. Then I see an x, I'm going to replace it with 2x minus 5 in parentheses, plus 4. And then I'm just going to simplify that. So I have a negative 6x plus 15 plus 4, which is negative 6x plus 19. So it's just like plugging in a number, we're just plugging in an expression instead. We're going to keep working on these because these ones are a little bit more difficult. If f of x is equal to x squared minus 2x, g of x is equal to x plus 5, and h of x is equal to the square root of x minus 4, find the following. First up is f of g of x. So that means in the function f, I'm going to plug in what g of x is. That's x plus 5. So anywhere I see an x in the function f, I'm going to replace it with an x plus 5. So we're going to have x plus 5 in parentheses squared minus 2 times x plus 5 in parentheses. So both of these x's got switched out for an x plus 5 in parentheses. The x plus 5 in parentheses squared means x plus 5 times x plus 5. And then if I distribute my negative 2 through, I have minus 2x minus 10. If I FOIL my two binomials together, I get x squared plus 5x plus 5x plus 25. I still have my minus 2x minus 10. And then if I combine my like terms, I'll have x squared plus 10x minus 2x is plus 8x. And then plus 25 minus 10 is plus 15. So x squared plus 8x plus 15. For the second one, we want to find g of f of x. You may be wondering to yourself if it will be the same as f of g of x. By the way I'm asking that, you're thinking probably not. Well, let's check. G of f of x, that means into the function g, I'm going to plug in what f of x is, x squared minus 2x. So where I see an x, it's now an x squared minus 2x. And then I have a plus 5 out back. Well, if I distribute the invisible 1 out front, I just have x squared minus 2x plus 5. And I can't simplify that, I'm done. And it is different. So f of g of x is not the same as g of f of x. I want to write that down because that is very important. F of g of x is not equal to g of f of x. There are some rare instances where it does occur, but in general, order matters when you're taking composite functions. Next up, we're looking at h of f of x. So that's going to be h evaluated at the expression x squared minus 2x. So that will be the square root of, I'm replacing my x with x squared minus 2x, and then a minus 4. Now, can we take the square root of x squared minus 2x minus 4? I can only take the square root of it if I have something squared, but not something that has pluses or minuses with it. It would have to be something in parentheses squared. So my question is, does x squared minus 2x minus 4 factor? Well, if I take my a times my c, I get a negative 4. Are there two numbers that multiply to give me negative 4 that add to negative 2? No. So this doesn't factor. Because it doesn't factor, we think of it as one giant group. So either we take the square root of that giant group or we don't take the square root of anything. We can't take the square root of that giant group because it's not something squared. Our x squared is attached to the 2x because of this minus sign. So you can't just break that part off. The pluses and minuses hold together like glue. So you can't take the square root if there are pluses and minuses involved. Let's try f of h of x and see what that one looks like. That'll be f evaluated at the square root of x minus 4. So that will be the square root of x minus 4 in parentheses squared because we're taking what we plug in and squaring it, minus 2 times what we're replacing, which is the square root of x minus 4. A square root and a square undo each other. They're actually called inverse functions, which is the very next section we're going to look at. But for now, we can think of it as undoing each other. And that leaves us with just the x minus 4 underneath. Then we have minus 2 times the square root of x minus 4. I don't have any like terms here because an x has an x, a negative 4 is just a number, and this negative 2 has a radical of x minus 4. Nothing else has a radical of x minus 4. So those are all different terms, and they cannot be combined. We're going to look at one more problem, and we're going to look at f of g of x and g of f of x. For this example, if f of x is equal to 1 over x minus 3, and g of x is equal to 5 over x plus 3, we want to find f of g of x and g of f of x. So starting with f of g of x, I'm going to start with my function f, which is 1 over. Now I see an x, I need to replace it with what g of x is, which is 5 over x plus 3. And then there's still a minus 3 from my f of x. So you'll notice that what I just wrote is f of x, but where there was an x is now the function g of x. I'm going to take those parentheses away again so that we can see what's going on. Well, in this giant denominator I have a plus 3 and a minus 3. Those undo each other. They cancel out. I'm left with 1 over 5 over x. But remember, if we have fraction division, a over b divided by c over d, we can do keep, change, flip. So we keep the first fraction the same, change from division to multiplication, flip the second fraction. Right here, this is just 1 divided by 5 over x. So that means I can do my keep, change, flip, and this is 1 times, flip the second fraction, x over 5, which is just x over 5. So when you see a fraction in the denominator, do your keep, change, flip, and all will be well. For g of f of x, I'm going to start with my function g, which is 5 over, I need to replace the x with f of x, so 1 over x minus 3, and then we have this plus 3 out back. I see a fraction in my denominator, so I'm going to do my keep, change, flip. So I have 5, it was 5 divided by, so change to multiplication. Flip this fraction, so it's x minus 3 over 1. And then my plus 3 out back is still just kind of hanging on. But wait a minute, if this is a fraction over 1, it's just the x minus 3. But be careful, we're multiplying by the whole x minus 3. So I need to distribute my 5 through the parentheses. I have 5x minus 15 plus 3, which simplifies to 5x minus 12.